Alright, so this is for Wiley number 5, and this was, I mean, I got the answers, but I had to, like, use the book, and I don't really understand everything about it, but anyway, so, let me just move this so I can write. Alright, so this was, question number 5 in Wiley. So it says, in the mass spectrum of 2,6-dimethyl 4-heptanol, there are prominent peaks at mass overcharge 87, 111, and 126. Alright, so it says propose reasonable structures for these fragment ions, okay, because they're ions. Alright, and so I notice that this is the same as question 9.33 in the book on page 446. So fortunately I was able to use the solutions manual to try to help me get through this a little bit, but it was still like really crazy. Alright, so here we have the pre-fragment, right? This is when you've just shot it with the electron and it lost one of its electrons and it's gained a positive charge. Right, this is the pre-fragment. This is the entire molecule. Pre-fragmentation. Okay, so count it up. There's 9 carbons times 12 equals 108. There is 1 oxygen times 16, which equals, of course, 16. I'm going to star that because of the oxygen can be 16 or can have the ion of 18. I didn't know which was which, and I figured it out a little bit later. And it has 20 hydrogens times 1, which equals 20. You add that all up, and you get a mass divided by charge of 144. Right, okay, so that little star that I put there, was it like 16 or 18 for the oxygen? I didn't know. Alright, so let's do the mass divided by carbon of the 87 fragment, right? So I took 144, which is the mass of this entire molecule, and I subtracted 87, which is the weight of the new fragment, and I got a total of 57. That means 57, atomic mass units, if that's what's going on, atomic mass units left, but they left as a radical, right? They left as a radical. They don't have any charge on them. So what I did is I said I have 57 mass. And the first thing I did was divide it by carbons. So each carbon is 12, and I got 4.75 carbons. 4.75 carbons could fit into 57. So I started out and I said, okay, let's pretend there's 4, because I can't do 5. 4 times 12 equals 48. And then I said 57 minus 48 equals 9. So I have 9 left. If 4 carbons left, then I have 9 atomic mass units to play with. And I said maybe those are 9 hydrogens. You know, it's possible. I guess because 4 hydrogens could take on 10. 4 carbons could take on, theoretically, 10 hydrogens. Yes. So 9 is not an outrageous number. So I thought about it, and what I did, I said, yes, there is a way to do this. So I wrote the molecule, CH3, attached here, CH3, here's this H, I just wrote that there. Carbon, which is attached to 2 H's, an H. So this has 1, 2, 3, 4 carbons and 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. And then I wanted to show the mechanism about how this happens. So in between the other carbons, I'm just going to write, I wrote the double bond, it's 2 dots. And then this comes over here, da, da, da. And then, right, this went over here too. And yes. Okay. So then, if this bond right here broke, and this gave one of its electrons here, and this sent one of its electrons here, and then this bond sent one of its electrons up here to the oxygen, that would give us this fragment, this neutral ion fragment. It's 57, and it's neutral. Now, I don't really understand why this carbon, why this isn't, it has one, whatever, I won't get into it, but I don't really completely understand why this radical is neutral, but, you know, it is. Alright, so then plus the charged radical, the charged particle that was left, it has 5 carbons times 12, which equals 60. It has 1 oxygen times 16, which equals 16. And it has 11 hydrogens times 1, which equals 11. And that gives me 87. Now that also answers my question about was it carbon 16 or was it oxygen 16 or oxygen 18, because the if it was oxygen 18, this would be 89, and there was no answer for 89. So, and I think in Wiley, with this one, Wiley was a little bit annoying with this because you had to write in, yes, I think it was, let me just look at Wiley real quick. Yeah, you have to put the, when you're typing this into Wiley, when you're typing this answer for MZ87, you have to put it just like this with the positive charge right here. Otherwise, it won't take it. So just, that's how you have to do it in Wiley. Okay. So then there was MZ mass divided by charge of 126. And here was the molecule that we were starting with, our beginning molecule. And, alright, so it's 126. First I said, okay, I took the mass charge ratio of my original, which is 144, minus 126, and I got 18. 18 in mass spectroscopy is a magic number because your M plus 1, what is this called? Give me 1 second. It's called something special. To determine molecular formula. The M plus 1 peak is not the base peak. What is the number? It's this is the mass peak, right? It tells you the mass. I thought it had a special name. Okay. whatever, doesn't matter. So this peak, your mass peak, your pre-fragmented peak, which is this up here, this is your m plus 1. No, your m positive, not plus 1, your m dot positive, your unfragmented molecule. Minus 18 is always going to equal loss of water, right? And I got that from page 434 in the book. Yes. So here your M positive radical is your pre-fragmented molecule, so that's your molecular weight. And if you're minus 18 from it, which we did up here, we found out that you're actually subtracting 18 to get 126, right? Because our fragment we're working with is 126. That means you have a loss of water. Alright, so now the mechanism. I kind of understood the mechanism. I got the mechanism for how to lose water from the book, but the eventual product I'm not 100% clear on. Alright, so this is from page, this is from page 434 in the book. So what they said, what do I have? Okay, I have here's my molecule. This goes to an H. Alright, and then this carbon right here is attached to a hydrogen. And this carbon right here is attached to this oxygen. Let me just put in all these. So basically what they said is that this hydrogen right here that's attached here gives one of its electrons to that oxygen and one of its electrons to this bond right here, and then this hydrogen obviously goes and attaches with this to become water over here. But before it can break off and become water, this bond right here, the carbon to oxygen bond right here, needs to give both of its electrons, so it's a double barbed arrow, and then it breaks off. So that breaks off and becomes water, and then what's left over, the book says, is so this here we see the electron. This is the electron that this hydrogen gave to this little bond here, and then this is positive because it gave both of its electrons to water so that the water could break off. And then something I've been trying to figure out that is really annoying and I can't really get it, and the mechanism of why they write it this way, and Wiley wants you to write it this way. You can't write this one, you can't write this way in Wiley, and I don't know why. I'm going to send this one to Allison because I really don't understand this and I want her to explain it. Alright, so the way Wiley wants you to write it is like this. You'll notice in Wiley, okay, it says, and then Wiley gives you these brackets. It gives you these brackets like this with this, the positive charge and the ion plus H2O, and they don't give you what's inside the bracket, but they want you to write it like that. Like that, or either with the bond here or the bond here. I don't think it matters. But that's the way Wiley wants you to write it for it to be right. And I'm going to send this to Allison and ask her why is this true? I just don't get this. Why does this become this? You know, explain that. And then finally, we had, I hope I don't run out of time here, M divided by Z, mass divided by ratio of 111. So, oh, maybe this is, actually 144. Actually, wait. I'm going to stop this right now because I think I see a little mistake I made.